I talked earlier about filter strips and the effects of buffered filter strips in an agricultural context. We can apply the same concept in an urban context, where we can begin to talk about runoff coming off of a hard-surfaced, developed landscape, slowing that runoff down by the way we treat the slopes coming into a low-lying area, trying to promote as much infiltration of water, storing the water as it moves along, infiltrating that water so that the amount of water that's discharged into the adjacent surface water system is greatly reduced. We are infiltrating and retaining moisture in the upland landscape. And the vegetation then is also providing water quality remediation. Because urban landscapes have a much more impermeable surface area than do agricultural landscapes and have higher runoff coefficients, generally speaking, urban filter strips need to be a little bit wider than is true of filter strips in an agricultural landscape. Regardless, we can talk about three different zones: the zone immediately adjacent to the sink itself, the zone immediately adjacent to the upland portion of the landscape, and then the zone in between. And the dimensions of these different zones depends upon the surface area that's contributing water to the system and what the level of precipitation is. We can talk about different filter strip widths, and in agricultural contexts such as this one, we can talk about approximately a 60-foot buffer strip to help promote retention of overland flow and retention of contaminants in the buffer vegetation before the water is discharged into the adjacent stream. So we're retaining water on site and we're treating that water. So we're actually dealing with detention, retention, and water quality mitigation. Another example of agricultural filter strips, forested filter strips on the left, in this case being used for timber production, and a grassland filter strip on the right. And again, depending upon the nature of what's happening in the upland area and the size of that upland area, we can have different widths of filter strips being needed. And I showed this slide again before. I show it again simply to bring across the idea that these filter strips are being used to catch the water as it's coming out of the agricultural fields, trying to infiltrate that as much as possible to slow down the rate of discharge and the volume of discharge and allow the adjacent riparian vegetation to provide water quality mitigation. In this case, a more popular concept that's being promoted now is to use these filter strips as an area to create harvestable biomass. We can talk about creating biomass energy from biomass from different kinds of plant material, and using these buffer strips along bottomland areas, along contaminant sinks, using these filter strips as an area to create harvestable biomass that can be transported to a biomass production plant and converted to bioenergy. So in this sense, we really begin to talk about a multifunctional landscape because we're getting food values out of the landscape, we're getting water quality and water quantity services out of the landscape, we're getting wildlife habitat services out of the landscape, we're getting biomass productivity services out of the landscape. So this becomes a truly multifunctional landscape. It's serving multiple social purposes in its construction.